So, hello and welcome back to Old School Coding. It's been a while. I have been doing live streams of the development of this simulation, and I figured this time I would go and do a recording to basically make sure that everything was good and review where we've done what we've done and where we've come from, kind of in a more compact format so you don't have to follow along with me for 3 hours as I ramble about this, that, and the other. This is a good checkpoint because we've come from starting from scratch all the way out over here. And we have worked our way up through simulating some signals moving and simulating the chip behaviors and then setting up this chip called an 8080 that has a whole bunch of internal state. And it talks to RAM chips, which have a whole bunch of internal state. And then there's semantics on top of that. Anyway, I thought I would do a quick overview of where we are and what we're doing and show the end product because this is really a nice stopping point for this particular direction. And we'll discuss where I might go next with this. So we can see there on the screen, the first thing I set up was a real simple clock generator where as the simulation progresses, it says, oh, it's time to push the signal high or push the signal low. And I actually have a nice little display of what's going on here. What we actually simulate is internally there is a clock signal that we're raising up and down and up and down. The fundamental unit of computation in this simulation is an edge. And you have a data structure that says, I am going to represent what's going on in a signal so you can subscribe to this and get called when there's a rising edge or a falling edge. And we've got one of these called clock. And at the root of the simulation, there's somebody whose entire job is to set the clock high and get a rising edge of the clock, and that percolates through the system. And then it sets the clock low, and that percolates through the system with a low dropping edge. So everything happens edge triggered. And what you do is you say, I have this function I want to run. For instance, Gen Phi 1 and Gen Phi 2 are driven by a bit of logic that says every time we get a falling edge on clock, I look at my little counter, and if I'm at the appropriate time during this cycle, I'm going to switch from Phi 1 high to Phi 1 low, and Phi 2 goes high, and so on. So this is a little piece of logic which is it's defined in two different ways in the 8080 documentation. First of all, in the documentation for the 8080 itself, it shows some discrete logic, which uses a 4-bit counter, and every time it gets to 12, it resets to 3. And that's really cool. And then they've got the 8224 chip, which I'm modeling this after, which does not disclose the exact logic that it produces, but it does have timing diagrams. And I was able to use those timing diagrams to derive precisely when these edges change, what the relative timing is, how long Phi 1 stays high and how long Phi 2 stays high, and the fact that they don't overlap, and the fact that these two edges, Phi 1 dropping and Phi 2 rising, there could be a gap between them, but in practice there isn't, and that there is a gap here. Timing of the status strobe, wildly different between the various definitions of this. The only important thing is that status strobe has to pulse low briefly at some point while the sync output of the CPU is high. So here's what we get from the clock generator. Now the 8224 also does some other things. It assures that the reset and the reset signal is properly latched. Okay. It holds the status strobe low until we're done resetting. So that's all in this particular thing here. And it also synchronizes the ready signal. So there's a ready input that comes from elsewhere. And the 8224 is responsible for latching that signal right here. So it's just after the rising edge of Phi 2. The ready signal will be set to its new value. Reset and ready are both latched right here. This is one main oscillator period after phi 2 rising, which is another reason why this is done in 8224. The other support chip in the chipset is the 8228. The main job of the 8228 is to observe the data bus and the status strobe. And when the status strobe pulses, it grabs 8 bits from the data bus, which represent internal state of the 8080. Things like, are we in M1 cycle? Are we doing an IO read or a memory read or an IO write or a memory write? Are we in halt and so on? There's a whole bunch of status. It's like a dozen combinations of these 8 bits that make sense. And its activity is defined specifically for those combinations. It says, if all 8 bits are in this pattern, we do this. It's not defined in the documentation as this output signal is this Boolean logic of these input signals, okay? Now, it turns out the equations are fairly simple, but you have to derive them yourself, and you are left with a lot of freedom of operation because any pattern of status bits that isn't one of the status bytes that the 8080 sends out, you're free to do what you want. So mainly it looks like this first one here where we have the data bus goes active with some value and the status strobe goes bimp. In this case, it's the value A2. We get hit with status strobe and then sometime later, data bus in goes high, and when data bus in goes high, we bring this mem read low. This differs from the actual hardware. The actual hardware brings, for memory reads, it actually starts this lower edge a lot sooner. I am deferring it to there because that makes things easier inside the system that I am building. Normally what you would do is when memory goes low, you'd look at the address and you'd start things going, and eventually DBM would go high, and that's when you'd get your data out. We also have hold. So if at any time during DBN HLDA goes high, we chop off memr, and the other ones are just the same. So these two chips conspire to assure that we have coming out of these 3 chips, the 8224, the 8228, and the 8080, out on the other end of it, these 3 chips, we've got a nice low-going mem read strobe, and a low-going mem write strobe, and a low-going IO read strobe, and a low-going IO write strobe, and a int acknowledge, which the simulation currently does not do either interrupts. It handles interrupts like this, but we're not going to do interrupts in the 8080. And we're not going to do a DMA. So some of the capacities of this chip will not be used during the simulation yet. Maybe someday we will. It would be kind of cool to set up DMA. Currently, every piece of software that I'm using on the 8080, all of the accesses devices tend to be, wait until we have a byte from a TTY and then read it, or give the disk controller this command and wait for it to finish. So we're going to do all of our IOs with PIOs, so some of this goes away. Anyway, that's the low-level stuff. So this gives us all of our signals. But riding on top of those signals, we now have the opportunity to build the 8080. There. So the 8080 is a central processor unit that fetches bytes from memory to boil things down. And the first byte it fetches tells it what to do. And that byte that opcode may have a couple more bytes of information. And generally it flows on to the next byte in memory after that. Boom, 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 boom. Does it sequentially until it comes to a branch. And here are all of the things that 8080 can do. The dashed lines are opcodes that do not have a defined operation in the Intel 8080. Other clone chips may do something useful at these locations. Certainly, when you start talking about the 8085, it fills in some, and the Z80 fills in more. Now, the 8080 has certain behaviors. Here's the behavior coming out of reset. Again, we're talking about this whole diagram here. Let me get rid of that. let's bring up the T-state diagram while we're here. No, this is not a useful diagram. This is something I was working on while I was trying to work out how to make things efficient. Let's just do that. So we can see as we are in reset, we've got our clock pounding away. Eventually reset in goes high, reset goes low. There's an internal reset that goes low. Status strobe was held low, which apparently in the hardware, the 8228 notices status strobe staying low and does a reset operation of some sort. Anyway, the 8228 chip has some internal state because it does some special things during interrupt. We're not going to be worried about that, but that's why that's there. So once we come out of reset, we get this normal pulse of operation where we've got CPU sends out a sync pulse, we get a status strobe, there's the address of the opcode, we end up getting a fetch. Now, in this case, we're reading from a ROM, so I am enforcing one wait state during all the reads. We are not handling wait states during writes or during I/O writes. So there's another way we're not quite complete. Now, I went down through and I basically went through all of the operations and set them all up and checked them by looking at the waveforms and saying, is this doing the right thing? Am I seeing the right values on the data bus? Am I seeing the right values on the address bus? Am I seeing the values change inside the registers? This plot that I'm doing is driven by trace data that I can capture during the simulation run. And we can draw single bit signals like phi1 and phi2 and ready and so on. We can draw buses like the CPU, the PC, and so on. And these guys can have a line down the middle saying either it's high impedance or we don't know what it is. Coming out of reset, we don't know what some things are. The contents of A is arbitrary until this particular time when it's got to have a 1-1, and so on. So that's all there. I think that I set up something so that you could even have a grayed out cross-hatched area to say that it's in transition or undefined or please don't sample this. So through all of the instructions, and you'll see that as things get more complicated, my plots start to get more crunched because we are looking at longer periods of simulated time and the clocks are starting to get mushed together. Let's scroll down a bit. We see all of the instructions. Well, I'm not sure all the instructions are there, but a great deal of them. A lot of my live streaming was working on one or another of these plots. So I would start up by simulating out the instruction and doing some testing and looking at the plot and working out that it was doing the right thing. In and out, for instance, differ from all previous plots in that they're now using IOR and IOW. Boom, boom. So we see that we're doing an IOW here and we're doing an IOR here. And I think that's the whole file. Yeah, I need to update this because these are no longer not yet updated. These have been updated. And I need to look up their plots at some point. But about the time I got these guys implemented and working, I started dealing with higher level issues. Like, let's actually write some assembly code. And I think that's where I left off. Let me look at my live stream logs here real quick. Boom, boom, boom. Lists. Old school coding. So the last live streaming I did, I was doing some refactoring. So we'd worked out how to get the 8080 to work. Okay. We then started adding other things around it. For instance, I have RAM array, which I did as one simulation module simulating an array 4 rows of 8 RAM chips, giving me 16 kilobytes of RAM and a ROM. And the ability to load from a .hex file into those. So I could take some assembly code that I had and assemble it for the 8080, get the Intel hex format file, and load that into a ROM, and we can go. Defined a character device, which we can see it here. Let me turn on the... This is a simulation of a simple printing terminal. And yes, I made it that color on purpose. I am of the school that grew up where my first computer console, well, actually my first computer console was punch cards and a line printer. But teletypes were the thing you would type at. And they used this really crappy rag paper that was kind of colored yellow. It was kind of thick and resilient, and Teletype Corporation apparently had been using this paper for forever. I thought of it as low-quality paper, but when it comes right down to it, it's nice stuff. Anyway, I got used to this whole black on yellow for that. I also have a CRT simulation. And yes, I am old enough school that for me, a CRT is green phosphor on a black background. So yes, I had a green screen. I was one of those fancy lads that had a green screen instead of using a normal television. The normal TV teletypewriters would be white on black. I used green on black. I thought it was great. Typically, I would have that much larger, but I wanted it to fit up in that corner there. And the other serial thing I did, this is a line printer. I couldn't figure out how to get the green bars to be alternating green and white. So 3 lines of green background and 3 lines of white background. That would be kind of cool. But the type is smaller because this is a line printer page. It's 132 columns wide by 66 lines, because that's the size of a line printer page, as determined by God. Okay, so those are all character devices. The interaction from the computer is we send them bytes and they display them, and some of them send us back bytes when somebody types. So let's turn those off. Actually, let's leave this one on. You can see if that's actually done something there. That's because after I got all this done, up through CDev, I wrote a really simple little monitor ROM, which just gives you a couple of commands you can execute. Now, my intention there was to start working on a full-fledged monitor ROM, so you could do things like read memory and write memory and debug things. And I thought, wait a minute. Back when I was at Sun, our monitor ROMs, while I was working on the Stingray and Galaxy projects, we shifted over to using Forth, because inside Forth, what have you got? Well, I can read blocks of memory and write blocks of memory and peek and poke at things, which is what you want to do when you're bringing up a new computer. So instead of writing a monitor ROM to do all these things, I thought, well, I'll just grab my copy of FigForth and make the small changes to it necessary to get it to talk to the simulation. So for instance, FigForth wants to call the CPM BIOS to read and write characters and to do disk reads and writes. I just rewrote that little bit of assembly code to do the inputs and outputs to get it to talk to the simulation, and Bob's your uncle. Got to get rid of editor temporary. Keep it clean. So did that and got it assembled. So got from an assembly file to a listing file and a hex file, and realized FigForth doesn't run in ROMs. You can make it ROMable, but if you are starting with an assembly code file, the changes to make FigForth ROMable are kind of nitpicky to get done. So I thought, well, instead, what I'll do is I'll write a simple boot ROM that allows me to boot from one of my disks. Okay, that's really all it does. I mean, I can halt, I can boot from disk, and that's it. And all the disk boot is going to do is it's going to select the appropriate drive 0 through 3, and read in the first 128 bytes. So the first sector of the first track. So it's sector 1, track 0, gets read into memory, and we start it running. Okay. If we look at the listing of this, there's my ROM monitor. Really, really, really simple. It got a little bit longer. I started adding some things to it. For instance, the ROM monitor has, it needs to get a line. It's not just I hit a key and it does something. I'm actually going to input a line and then work off of what does this text line tell me to do? And oh, the first character is foo, we're going to do something. I wanted to allow for extending this ROM monitor rather than just having it be, press the key for the drive you want to boot from. Oh, there we go. And we have, this is my test bed for debugging my CDEV stuff, making sure I could read and write characters to the various things. So TTY, I believe I've ripped out most of it there. Yeah, we do a TTY get. We've got the ability to get the next character. This will stall until there is one. Putting a character will stall until I can send one. Send out a string. We've got an inline string, so I can say call TTY ILM and have this string right here inline in the assembly code. Makes it really easy to print messages from this monitor. I've got like 2 messages I print. Yeah, very important to make that easy. Do boot. Basically, we reset the simulation. We reset the simulated disk controller. In case the disk controller has internal state that we need to reset, this code doesn't get to know whether we do or not. Set the drive, pick an address, which I'm arbitrarily putting at 80 hex. So we're not going to touch the first 128 bytes. That's where RSTs jump down into 0 and all the way up to just below 40 hex. It's kind of convenient to put it at 80 hex. Once we get to where we're thinking about booting CPM, that puts it nicely. Coming at 80 hex here, CPM is going to lay out, and then we're going to relocate it to the right place, or we just load it to the right place. We'll worry about that when we get to CPM. But 80 hex is a nice buffer area. For fourth, the fourth assembly code I have was intended to run under CPM, so its origin is at 100. I thought, well, if I keep the origin at 100, I'll be able to compare the printouts that I have from 40 years ago with what I'm doing now. So that's where it is. And this basically just says load bytes. So get a byte and go do it. So what if we actually boot it? I am going to hit A. We're going to boot from drive A, which is the first sector is going to have some extended boot code. This only loads up one sector. So the first sector of the disk needs to load the rest of it. And that means that for fourth, I can bring it into 100. CPM can bring it into wherever it needs to bring it into. And it knows that boot sector on the disk knows how much more data on the disk is the thing to boot. What's that going to load? It's going to load this boot fourth. That's the whole thing. This is modeled after code from 40 years ago. Obviously, it's doing something a little different because it's talking to the simulated disk controller, which always has, once you've told the controller what you want, the simulated disk controller always has data ready. So normally in a PIO situation, you would read a status word that says, "Are you ready yet?" And at some point, the status word would say, "I'm ready," and then you would start moving bytes. Or for any number of reasons, what you would really do is give the disk controller a command that says, this track, this sector, put it there, go. And then later you get back an interrupt that says, we're done. Not doing that. Anyway, so this guy says, basically, I set up so that I could read the configuration of the bootloader from memory. So I point my stack pointer here at this stack, and then I pop from it the various parameters. So the first thing I pop is transfer size, bytes. We can patch it. Okay, so boot sector, the last three words of the boot sector are going to have transfer size, where the image should go, and where we should jump to when we're done. The rest of this doesn't change. So we can have this to boot Figforth. We can have the same code to boot CPM, and all we do is we change the cold start configuration table. And once that runs, it's all going to happen very fast once we get to actually executing it over there on that yellow screen. We're going to branch into this beast. This is Figforth for the 8080, version A0, dated 17 September 1979. Now, in September of 1979, I was starting my senior year of high school. And our high school had a Sol 20. Later, I purchased that Sol from the high school. And I kept that through college. I guess I have added a little paragraph here saying, yes, I am modifying this. The rest of this, I kept all of the comments intact. I found a copy of this on the web, which is why I got all the text. I have a printed copy of this document in a binder, which has survived fire, flood, move, and so on. I still have it. So I was able to then cross-reference with the actual printed document. We're using an assembler called ASL. Very nice, which appears to have some differences from the CPM assembler, which we'll get to. I'm not going to go into detail of Forth works. That is that's a whole new series of videos. I could dive into Figforth and spend days on this. But the net effect is that we're going to jump into a threaded interpretive language, where you type words. Each word you type has an effect. You've got a data stack. And if you're doing math, it's going to take its operands from the data stack and push its result back on the data stack. And the way you write a program in Forth is to concatenate these words and say, do this, then do that, then do that. And there's looping constructs and conditional constructs which can do things for you. So it becomes a Turing-complete programming language fairly quickly. This whole thing, all of Forth, fits under 1A80. So 1A80 is as far as you can go and fit on 2 tracks of an IBM 8-inch single-sided, single-density diskette drive. 2 tracks, or 1 track for double density. I don't know if this was intentional or not. Let me check my printed document real quick, see if it might have been intentional. Just to show you what we're working from. This is the document. You can see it has all sorts of fire and smoke and water damage. I have to be very careful. But I worked from this document to get Figforth running on a Sol 20 with 32K of RAM going. I had to rewrite some of the I/O stuff to talk to the Sol's ROMs. So I can look at the end of this document. I'm beginning to feel like I should be using nitrile gloves when I start touching this. Some of these pages are so... It's all still readable, but you would never be able to get a scan from it. So here's the memory map. I don't know if that's readable at all. This tells you the initial direct dictionary pointer for the stock fig-forth was 1A88, which means that you couldn't take this image together with a 128 byte loader and fit it on one track of a IBM dual density diskette. Okay, so it's just because the machine I'm porting to has a very efficient way of doing I/O, that got smaller, and it brought us down underneath the limit. Now, I actually compute at the end some things. I added these things. I said, well, the boot size, boot image is 128 bytes of boot sector plus span from init DP down to org. So I compute that, and then I said, well, how many sectors is this? 128 bytes per sector, rounded up, 34H sectors. So that's 52 sectors. Well, 52 sectors is the number of sectors on a double density IBM diskette. Yay! Doesn't matter for the Sol because what I didn't have was 8-inch disks on that thing. That had a Micropolis 5-inch disk drive. It had one 5.25-inch floppy disk drive. For a while, I had access to a computer with a pair of 8-inch floppies. It was a Stratos Z80, very nice machine. Z80 with 80 kilobytes of memory. It uses some memory banking to get things going. Works really well with CPM3. They had multiple track buffers that they handled in their ROM aside from what CPM knew about. Just very nice, very slick. They lasted a couple years, then went out of business. Too bad. That was the era of hundreds, maybe thousands of companies all building 8080 and 8080-like machines that were very different from each other, but they all ran CPM. So back to our fourth here. It's actually a boot. There it is, fig-forth 1.1. Now, vlist, that's all the words in fig-forth. I remember when you're looking at this on a CRT screen that is 16 rows by 64 columns, this is several screens scrolling past. It looks like it's a lot of words. But looking at it on a teletype, where you've got 80 columns, and you've got as many lines as you want because it's a frippin' scrolling piece of paper, that's it. Now we can write some real simple forth. Let's write countdown. So I'm going to take a number, I'm going to count down from that number to 0. Oh, silly me, I'm going to count up from 0 to that number. Anyway, so you got the whole thing. I can go into hex mode. I can say I want to look at some memory. So let's say I want to look at 0500. Oh, wait a minute. You can't put a do loop on the terminal. So let's write a memory dump thing. The memory dump, I'm going to take an address range, start to end. And the do loop is the starting value has to be at the top of the stack. So we're going to need to swap and increment by 1. Actually, increment by 1 and then swap. Okay, so now we're inside a loop where I is going to be our address. What I want to do is I print blank, and then I'm going to do a I fetch dot cr loop. Before we loop, though, I'm going to say if terminal, if there's a character available in the terminal, then leave. oops. Oh, screen number 4 has some messages. And if you put a 1 in this thing called warning, it will do the right thing for you. So, yeah, I forgot to put an if in there. So let's do this. Mdump. Okay, u dot bl I fetch u dot cr. Then we're going to say question terminal if leave and if. Okay, so starting address, ending address, mdump. Real simple memory dump. So these fetches, mdump has a bug in that I am fetching a word at each address. So this is not a really great memory dumper. Anyway, once you get comfortable with Forth, you can use it to bring up new computers fairly quickly. So currently, I am running a Forth that came from this assembly file here. What I would normally do at this point is divert over and get running a Forth that is mostly written in Forth. So I can modify the Forth source code for my Forth and reload it and change my Forth image over time to tune it to what we want. And in fact, you can write things in Forth. For instance, this is a complete assembler for the, which goes with Forth. So you can write assembly code in Forth. Didn't think you'd see a macro assembler written that fits on one page like this. And 9020 index. We also have a line editor. I'm not really good at using the editor, but it's got commands that you can use. To edit these screens. Currently, what I'm doing for these screens is I put them in a text file and I have a program that loads them into disk. So this means we are basically up and running on Forth. Now, I did my initial debugging on Forth by being invasive. I put an instruction in Forth inside next that would trigger the simulation to dump a whole bunch of state, including Forth state. So looking at things like the Forth data stack and the Forth return stack and decoding, knowing that BC pointed to my instructions, decoding what was going on. And I did that until I basically had a working Forth. And then I was able to shift away from that, go back to stock Forth, and debug from within Forth. So if you look near the bottom, there's some words, like list, for instance. There was some problems that I was encountering in not this code, but other code. So what I ended up doing was bringing in a comment that said what the word was. I grabbed its definition from the glossary, so I knew exactly what it was supposed to do, added some implementation notes as necessary, and then brought in the actual Forth source code that produces these words. Stare at this stuff, and I found some problems. One problem was self-inflicted. Forth has a way of saying block offset within disk. I thought, oh, I'll reserve the first 4 kilobytes by doing a block offset. Well, typically inside Forth, block offset is 0 for disk 0. So when you want to print a message, remember I said something like 12 message prints that message out from screen 4. Wherever you are, what it does is it negates the offset to get you to screen 4 of disk 0. Because Forth wants to think of all of your disks as being a contiguous array of disks in a linear space of screen numbers. So by using offset to reserve the first couple of tracks on the first disk, what happened was when it printed messages out, it got binary crap. Anyway, had to debug that in Forth. Simple enough. But that means what we've got here is, ignoring all of that stuff, all the details about Forth, we have a working Forth, which means we've got a working CPU. Oh, we did find a bug in the CPU. Let's bring it up here. Inside the ALU, where I was setting the ALU flags, I was setting Z wrong. The buggy code looked like this: Z equals ALU. So that's like dead simple. It says if the ALU is 0, set the Z flag. What I forgot was the value coming in for the ALU also contained the carry flag. It was the extended ALU result in 9 bits, which includes the carry in bit 8. So any ALU result whose extended value was 256, I would not set the Z flag. Well, it turns out that if you are comparing 2 bytes ignoring the top bit, the easiest way to do that is to subtract them, then do it, add A to itself, which comes up with a 0 if A had the most significant bit set and nothing else. Adding A to itself should turn on the carry, and it should turn on 0, and it wasn't because that line. That took me a lot of hours because I thought I had a bug in Forth, and it came down to there was a JNZ which was executing when it shouldn't. And it took a while before I realized that it was that add instruction that wasn't setting the Z flag because the result was 256. Dope. Anyway, so that was the only actual debugging I got done here. There was a bunch of things I completed. There's actually a big old commit that I did called The Rest of the Owl, which includes a whole bunch of messing around that I did while I was trying to get Forth working, while I was trying to debug what was going on with 2 things. First of all, there was this problem of the Z bit not being set. Other one was, so let's look at the list file. LST file. We look at the fig Forth. This still has the, you notice here in fig Forth, uless, DW zbrand, uless minus $sign. That says, basically we're encoding a word that says this is a branch on branch F0. The following word is an offset to the destination. So it should be 1, 2, 5, 6. Times 2 is 12 bytes. Instead, it's got 14 bytes because the assembler, ASL, $sign is the address of the DW, not the address that we're sending it. But if we look at the original, very near the bottom, there's the original paper copy. Okay. Make sure this is the branch to uless minus $sign. The original paper copy, this value is 0C00, not 0E00. This was a 2-byte offset error, 1-word error. So every branch and conditional branch, everywhere in Forth, it was written as a DW with a comma like this. Always branch to the word after the word it was supposed to branch to. But the ones that just said DW that didn't have the comma there, that had the destination on its own line, those were correct. Okay. So now if we look at what I have done for the void star Forth, All I did was split that line to put u less minus 1 to dw, put it on its own line, and now I have the correct value. I couldn't believe it when I cracked out my printed copy and compared them, because the original file that I picked up, I actually got my copy of Fig4th from the net. I picked up a file that was the output of an assembly Fig4th, and son of a gun, it had the E value here. It had 92010E00, so it had the wrong offset. And that was an archival copy of a listing. Apparently somebody assembled forth with an assembler that used the wrong dollar convention. And we've been working off of that list. I don't think anybody working from that listing actually got it working. So I didn't see anybody that split this, but it's working now. Anyway, so from scratch, we're building up signals all the way to having an interactive fourth here. Boom, boom. All those words available. We can look at the disk. We can talk to the disk. Do I have anything on the disk of interest? 9150. Okay, I started putting in the fourth model itself. 97. Okay, so part of the fourth model is fourth in fourth. And I'm trying to get it set up, and it's all manual typing because I couldn't find a copy online. I haven't found a copy online yet, so I'm typing it in from my printed copy. Worse yet, it's actually for the 6502. So there'll be bits of it that are for the 8080 that I can, well, that are in fourth that I can use. I'll have to leave out all the 6502 stuff. But we're going to get there. And the last thing it does when it's all done, after it's compiled all of fourth from fourth, 80, 96, and 97 list. Oops. 96 index, 97 list. So it does a whole bunch of things. At the end of the fourth image from the model, it does include this editor. And last thing it does is backpatch the initialization data to set it up so that when you boot the image that you just compiled, it does the right thing. .497 index. The model itself stretches all the way from screen 3 or 4. Let's see, let's go from 397 index. So all of those will be filled in. Now currently, screens 6, 7, and 8, I've dropped the assembler in. Those actually have assembly code in the fourth model for the wrong CPU. I figure I could start by putting the assembler in from John Cassidy. And then he has some examples that he published in fourth dimensions that I've dumped in here in screens 51 and 52. Anyway, this is going to be slow going. So if you're writing assembly code in fourth source code, it looks like this. It's all RPN. So instead of hop H, it's HPOP. LA move moves from L to A. HL move moves from H to L. And so on. PSH1 is a label, and so on. Anyway, so this is what your assembly code looks like. He set up for some structured coding. So we have while repeat. We have if then. So if then, when you do an if, it simply remembers where you are. When you do a then, it plants a branch back to if. So conditionals, if, oop, we do, oh wait, I'm sorry, the other way around. If then says, we have a condition on the stack. We we assemble the correct conditional branch, conditional jump. We get to then, we now know the destination. We go back patch the conditional jump. So kind of clever that all this happens behind the hood in those very compact assembler to get us assembly code with if then and while repeat and begin repeat and so on. I may be reading this crazily. Dpop, hpop, begin, da move, while. I may have to go back and review what his structuring conventions are. But basically, he gets you away from having to set labels and do jumps for local loops and conditionals. Good stuff. Anyway, so that's where we are now. I will pick up with the live streams on doing something extension of this. Maybe I will go into what can we do in fourth. This is currently running at about 5 times the speed of the original 8080. There's also, what other things can we simulate? Can I go from an 8080 to an ARM? Okay, that's a big jump. Maybe I want to go from 8080 to a Z80 first. Maybe I would want to do a 6502, although back in 1980, I did not have a 6502 that I worked with. I had a friend with an Apple and a friend with a TRS-80, and I had the Sol, so we did things back and forth. The only thing I did on the Apple was I worked on a program on the Apple in a higher level language, but at the lowest level, I actually rewrote part of the disk controller to do what's called quarter tracking. We wanted to write that code ourselves. This was for a commercial project, which wanted to do some things to obscure what was on the disk. And we worked out how to set it up so that as you read the tracks, you'd read the first quarter of the track, and then you'd step by a quarter of a track. Second quarter of the track and step by a quarter. So what happened would be, if you tried to read it normally, most of the data wouldn't be well under the head. And in some cases, your head would be halfway in between where the data is actually recorded on the media. Very, very weird stuff. But it only worked because I was on an Apple and I had absolute control over the hardware. It was really fiddly to get going. And I think we ended up changing things around a little bit so that we actually ended up with less data stored on the disk because we had some time spent stepping the head. But it seemed to work. We were able to reliably read and write our data to and from the disk, and the stock Apple code could not read our data, and that was the intent. Anyway, so that's the only thing I did on the 6502. The other one I might want to do be an 1802, because some of my early work was with an organization that built alarm boards. I believe it had an 1802 in it. I didn't get to touch that code. That was all Tom Pittman's work. So he kind of came in and out, and I never really got to know him or meet him more than once or twice. But his code managed to fit inside this tiny ROM and did all sorts of amazing things. So I've always wanted to dive into the 1802. So essentially, we could simulate other CPUs. Moving forward, it'd be kind of cool at some point to simulate a Spark v7, although that's a very large chip with a very large instruction set. So that'd be a major undertaking. I'm not sure I'd want to do that using these techniques. I think I would want to go to C++ and start bringing in all sorts of more modern engineering techniques that would kind of violate the spirit of the channel. So we'll see where we go next. I'm going to seal up the project as it sits because it is currently working. I will leave a label. I'm going to set a tag on this. Once I've verified that everything is cool, I'm going to run some more testing on it. Make sure everything is working properly. One potential thing I could do branching from this point in the project would be to set up Metaforth. I looked for copies of Metaforth online. Probably I've been looking for a couple of years now. I have a printed copy. It's in pretty bad shape, but I can read it. It's a lot of text to type in, and since I don't find it anywhere on the web, I am wondering if there was a concerted effort to prevent it, because every reference I have is, send $30 to John Cassidy. Now, if I knew where John Cassidy was, I would be happy to send him $30 for a machine-readable copy. I have a printed copy. I found it. So the question now is, can I get a copy of it online somewhere? Is it available? Do I type it in from the book and then study it and understand how it works and revise it to match? He makes a point in here. This is not a load and go thing. This is something where he is exploring how you do it. And you're supposed to take your Forth source code, which in my case would be the same he started off with, and do it. So his printed stuff should be very close to what I need. I would have to tweak it for talking to my I/O devices, but that's it. Used a Poly 88, which is a nice machine and everything, but it's got different conventions for how to talk to disk controllers and so on. That's easy to change. But I think between Metaforth, the 8080, Cassidy, and the Figforth model, which is for 6502, which contains all of the Figforth standard words, got a leg up there. So maybe that's a project I could do here, get that going. Not so much old school coding as fourth school coding. From what I'm seeing, there are still a few people out there that use Forth, and they still stick to kind of the same ideas on how to develop that they've always had. Forth is more of a state of mind, a philosophy. Chuck Moore had some interesting ideas, and they played out nicely in Forth. Not sure how well they apply if you're trying to produce a code in like C or Rust, but for Forth, perfect. Anyway, so that's it. I am going to call this a recording. I'm going to go review it, make sure things came out okay, and you'll see this on the channel when you see it. Talk to you then. Keep it small, keep it safe. Right.